Yeah, please, visible. A very good morning to you all. In line with the control of voltage and reactive power, we are likely to understand the different methods how voltage can be controlled by the injection of reactive power itself. We are very clearly known to the peculiar interconnection of active power with the frequency and reactive power with the voltage. In line with that, how is that voltage profile of the system is managed by incorporating reactive power management? Having injected or managed it to the suitability by switching action, how voltage is appropriately maintained within the specified limits. In line with this, we have three broad headings. One is shunt capacitor or reactor, a technique of injection or absorption of reactive power, and series capacitor for a long transmission line to compensate the inductiveness of the long transmission line by adopting capacitors in the series part, and synchronous condenser where it is a synchronous machine working with no load on the shaft with the various excitation mode. Under excited, over excited mode of operation definitely make a possibility of injection of reactive power to the system and absorb the reactive power from the system. So this is how these three different methods highlight how reactive power injection supports the voltage control in this way. In the examination, you might be having a question, explain any two methods, explain the following, like that. You may find a statement and you may need to present the content for the suitable heading. In that perspective, let us take the first one. How is that shunt capacitor based capacitor and inductor based concept work? So let's see approach. When I have a shunt capacitor or reactor, definitely a system having interconnection, we can see a single line diagram in the image A, sending end and a receiving end, and a transmission line XL with the reactance represented here. Definitely at the receiving end, if the profile of the voltage is not maintained within the range, that may be due to highly inductive loads or ill-conditioned system. To compensate that, because of that highly ill-conditioned system, what we notice is highly inductive current or a lagging power factor at that system. Then to compensate that, leading volt amperes need to be incorporated at that point. That means if the system is highly inductive, to compensate that, a capacitive reactance or capacitor, if I incorporate at the optimal point, let's say at the bus itself, it is marked as a capacitor inserted, which will definitely make leading volt ampere. Hence, you can see the voltage VR, which is the receiving end voltage, and the sending end voltage Vs, and you will find the current flowing through this capacitor which is installed. The shunt capacitor at the load side itself having leading current with respect to voltage. That is shown vertically upward in the vectorial representation. And this leading current with I charging or I capacitor into XL compensate this VR down to Vs. So it means to say this drop is compensated by this reactor, it means inductor itself, capacitor which is connected to bus itself. It is just to say shunt reactor and capacitors either permanently connected to a transmission line or they are appropriately switched on or off as and when need arise. The total effect of connection of capacitor to the line is to compensate lagging VAR with the leading VAR what we switch to the line, such that the compensation which is adopted will improve the voltage profile. It may happen like this way. When a transmission line is delivering highly inductive load, quite natural, the lagging VAR definitely demands compensation. Suddenly load is withdrawn or load is declining. The compensation what is being adopted to the system lead ahead. Again, that affects the voltage profile of the system. Then it needs to be absorbed or it needs to be suitably controlled. In line with which we have these capacitors installed need to be removed or added inadequate to that, As well, inductor which were put in parallel to this capacitor need to be switched on so that they start absorbing the leading volt ampere which is available in the system. This way, a shunt capacitor or a reactor based concept, by switching those capacitor or inductor on the need or specific to the requirement, which can compensate the reactive power balance. Then it is being shown very clearly with the receiving end open, the capacitive charging current, which is say ICH. When the receiving end is open, the current drawn, which is leading with respect to the receiving end by 90 degrees. Current through capacitor with respect to that voltage applied with which definitely make a leading 90 degrees. And definitely we will find the drop which is caused over here is ICH into XL is in line with the phasor sum of the VR and ICH XL. So which gives VS. We see VR is greater than VS in this particular notation. So this way we can just see to it that due to the absorption of inductive or lagging VAR, we need to compensate by adopting leading volt ampere by capacitor. Suppose load is suddenly removed, which was already compensated by adopting compensator, we need to absorb it either by hooking up inductor across a particular bus or eliminating the capacitor in part. So that's why this method is one of the simplest methods practiced in highly inductive load, large industries, where we find induction motors in large number. Higher capacity induction motors being switched, definitely that absorption and that effect on the local system adversely cause their total operation or the high suction of current during the starting makes the building or their total system going little inferior. In such scenario, local compensation at the load terminal itself is done by compensating by capacitor itself. So this is not going to compensate the particular total reactance. As and when there is a load compensation is taken immediately by that way. This is one simplest method, hooking it parallel according to the computed leading volt ampere as per the requirement. That has to be balanced by your suitable switching mechanism and control. So still better than this, if you could see series capacitor approach. So I have this next phenomena. The shunt reactors of sufficient size must be permanently connected to limit fundamental frequency temporary over voltage about 1.5 pu or less than, for less than 1 second. This is very interesting aspect. When we have overcompensation to the system, highly inductive system is highly compensated by a capacitor, what may happen? Due to the sudden removal of the load, voltage overshoots. Those temporary overshoot of the voltage on removal of load may go 1 pu and beyond its capacity. That's what meaning. You should be very careful to install reactor such that the overshoot of voltage over 1.5 pu and above shall not go more than 1 second. Within a second of observation, the overshoot has to come down to nominal voltage very closer. In this regard, even the removal of capacitor may not support. The addition of reactor to absorb spontaneously along with the removal of the capacitor might work in coordination. So that's why series reactors are also important as shunt reactor are also important like our shunt capacitors in this context. And switched reactors are connected to extra high voltage bus to maintain normal voltage under no load or light load conditions. This is another approach. You can see one single line diagram which is shown here. So a system, a weaker system, a stronger system interconnected, and a transformer if there is in the system. The primary, secondary, tertiary. The tertiary winding is meant for compensation. Most of the compensation through the transformer is done at tertiary winding only. This is going to cause the phasor changes in the reflections at the primary and secondary. So therefore, tertiary winding is adopted with the compensating devices. So you might be known to this. Whatever the compensating devices incorporated at the transformer or through the transformer or basically at the tertiary winding. Primary secondary. Primary is the one to which it interfaces as an input, secondary from where power is drawn out. The tertiary is the one which is left for the control of that. So therefore, this tertiary winding is equipped with controlling concept, either like a inductor, capacitor, or any devices which are going to go for compensation of the requirement like this. And this diagram highlights you how is that permanently switched inductor and a switched inductor. So whenever there is a need, it will be hooked on. You can see the weak system also. Like this, some of the things are permanently hooked. Some of the reactors are shown open on the need. Whenever the compensation is overcompensation has been seen or load removal has come to compensate that state of the system, these switches need to be closed in a systematic way. This way, shunt capacitor and shunt inductors are very important in managing the required reactive power as per the required injection as well as absorption to maintain the voltage profile of the system under the control. Then series capacitor, another important aspect which is a series capacitor. This is a very strongest mechanism of control of reactive power or reactance of the line. As we say, a transmission line is highly inductive in nature. How do you reduce that inductance part of that or reactance of that? By making a counteraction on that. By making a counteraction on that such that the highly inductiveness, the XL part of that transmission line is compensated by inserting a series capacitor along with the section of the transmission line, where XL of the line, XC of the compensating capacitor, each together result the magnitude of the remaining system's reactance. So with this way, a very strong compensation to the transmission line is possible. But the only drawback of this system is the capacitors or compensating components which are inserted in series with the line experience the fault current due to any fault which is running on the line, so they may get affected. This will demand additional protecting mechanism on whose occurrence of a fault compensating devices need to be isolated from the system. This is an additional need for the protection of compensating components, because the compensating components like the capacitors are put in series along with the transmission line. Whenever there is a fault in the system, fault current do run down to the point of fault. May it will be running through a capacitor. This capacitor may experience high stress and may burst or expose to the fault. In such situation, we need to protect the capacitor with the additional switchgears or mechanism. That is the disadvantage. But the advantage of this mechanism is very strong compensation is possible, and it can be definitely become one of the substitute for a long transmission line. Suppose if you look into a power transfer between any two buses in a power system, having voltage of one bus is say V1, voltage of another bus is V2, connected to a reactance or transmission X12. The power transfer between those two is given by P12, V1, V2, the magnitude, sign of the angular difference between the voltage vector V1, V2 like that, over X12. This X12 is say highly inductive. You can imagine this is in the denominator. Highly inductive reactance or highly larger value of X definitely makes the P12 limited. It limits the P12 to a smaller value. Hence, the strong compensation is highly possible if this X12 is minimal by value. So this minimization of X12 is possible by insertion of series capacitor. So therefore, counterbalancing or counteracting reactance which you need to eliminate, that much value of capacitive reactance must be adopted such that the net reactance of the system reduces and power transfer ability superior in the way. Then a series capacitor would partially compensate X12 and thus increase maximum power transfer that can be transmitted, reducing effective reactive power loss. Because when the total reactance of the system is getting decreased, we can say I square X loss, what would happen? current flowing through that and reactance offered with the next sectional path x after xl minus xc. If you say reactance dominating at that time, I square x is definitely minimal. So then in other way, the series compensation reduces the line voltage drop. Yes, because reactance is minimized, the drop due to the inductiveness is reduced. Limits the load dependent on voltage drop. It limits the load dependent on voltage drop. Influences power flow in parallel line, because it is definitely going to cause a better phenomena and influences the power flow in parallel line. Increases steady state power transfer capability. For a given power transfer, reduces the transmission angle, because this angular difference delta 1 delta 2 what we are speaking. So this angle is also influenced by the total reactance of the system. So increases the system stability. When we speak about stability aspect of a power system, it is an ability of a system to be in service even after encountering any fault, disasters, or any specific adverse situation. So that ability concerned to the voltage will be stronger with the system if incorporation of series capacitor to compensate works out. So in this way, a comparison of series and parallel capacitor can be taken into case. Then I have one more reviewing here. When I incorporate, let's see a series capacitor concept. You can see sending end voltage, receiving end voltage bus, or you can say bus receiving end, bus sending end, and you have representation of total reactance of the line by XL. XL represents entire transmission section's inductive reactance. Let's say a capacitor XC, a reactive term XC is inserted. Then without this insertion of capacitor for the compensation, with the insertion of capacitor for the compensation, let us see how is that viewed with the vectorial representation. Let us view the receiving end voltage VR, and from the receiving end voltage we will construct what is the value of UF, what is the profile of sending end from reverse. Let's say a vector which is shown you here is VR. VR is the receiving end vector, and there is a draw of the current which is inductive, IR lagging with the phi. So you can say phi IR. Then this transmission section is shown with only inductor. Let us say capacitor concept is not there initially. Capacitor is not there. Only XL is there. Therefore, resistance part of the transmission line is assumed to be 0. Only inductance is considered. Then we have current what is being flown at the load is IR. IR into XL is the drop what is encountered in the system before the compensation. You will find at the tip of this vector VR a vector IR into XL. You can see a large length which is shown over here in the parallel. IR into XL is the drop happening in the inductive reactance. IR into XL, which is joined to the tip of the vector VR in perpendicular to IR. Because current through inductor, voltage across the inductor, if you compare, there is a 90-degree difference between those two. Current through which lags behind the voltage, or voltage across the inductor lead ahead of the current. That's what. Current is taken perpendicular to which a vector of IR into XL is represented. When I join that, it will become a sending end voltage. You can see by the graphical representation, magnitude, if you visualize Vs is nothing but magnitude of the sending end voltage. That is without the capacitor or a compensation. So this is the representation. What is that? Sending end voltage to be maintained, to retain certain VR at the receiving end. For the retaining of VR magnitude, Pu, whatever the value of receiving end voltage, what must be the sending end voltage profile after taking care of the drop, what would encounter in the path? That's what is VR plus IR into XL. When I join, I'll be getting Vs. That is the voltage which the sending end has to manage such that VR is available at the receiving end. So this is due to uncompensated state of the power system transmission section. Suppose if we adopt a series capacitor concept, let us insert a capacitor Xc, capacitive reactance Xc. Let's see the capacitive reactance when it is inserted in series with the line, current flowing through the capacitor and causing IR into Xc as the drop. Then we will find the reactive side IR into XL, which was shown here earlier with the extended side in perpendicular to IR, now get compensated by IR into Xc in a reverse manner, so that there is a removal of certain reactive drop. IR into XL, originally what it was a very larger magnitude, is getting eliminated by IR into Xc. Then the resultant IR into XL minus IR into Xc is the resultant voltage drop. That you can see a solid line represented here. At the tip of the vector VR, a small length which is IR outside the bracket, XL minus Xc is called the net drop after the compensation with the capacitor. So that vector point or that point, if I join with the origin, you will find profile or the magnitude of the sending end voltage with the compensation. So visually we can find a tremendous change in magnitude of Vs on a system without compensation, Vs with the compensation. So therefore, it's very superior and very stronger compensation for the long transmission line where system is highly inductive in nature. So therefore, IR XL and compensation after IR Xc result you a small drop IR XL minus Xc, which makes the voltage of the sending end very superior. So in this way, the compensation by series capacitor is very stronger. You can see the 3 points which have been mentioned here. Rise in voltage on one step of capacitor is due to the line reactive current during power swing or heavy power transfer. This may cause damage or stress on the equipment on side experiencing high voltage, implying higher rating of them. So therefore, there could be an again alert. So these capacitors, due to imbalances at either side, get stressed. In case of short circuit on the line, voltage across the capacitor tend to be much higher across this and cause a damage to the capacitor. So this needs to be protected from that. And location of capacitor bank influence the cost, because the transmission line where you are installing it, how you are maintaining it. So all those position and value definitely matter. So the location and capacity of the capacitor also matter, and protective mechanism which we incorporate also very important. Therefore, the series capacitor compensation is no doubt stronger compensation. Suffer some of the problems that technically one need to take care. Those are protected by the lower two diagrams. You can see there a capacitor which is inserted for the compensation should have spark gap across that. So it is, you can see here G1 spark gap high set, then G2 spark gap low set, and we have switches S1, S2 like a circuit breaker contact closing with a damping circuit, which protects this capacitor by bypassing them on the situation which is going to occur. So we should have control circuitry which will trigger these things such that capacitor is bypassed during such adverse scenarios where it is sure to get lost, damaged. To protect that capacitor, such an infrastructure needs to be incorporated around this capacitor so that capacitor will be in service even after experiencing such an worse scenario. By these, it is protected. So like this, we have capacitor need to be bypassed and need to be closed. You can see, suppose reference switch is closed. You can see the current flow through this way, like this flow. That is called as reinsertion breaker or bypass breaker. So these are such a way suitably operated such that capacitor is protected from such experiences in life. And then again we have a capacitor bank. Suppose we have capacitor bank as damping circuit which will protect this by operation, and we have spark gap, bypass switch, and non-linear resistor across. Just to protect this on across section over current, definitely it will make it to isolate by the circuitry. So it means these are the protective mechanisms incorporated to isolate this capacitor during its adverse scenario, keeping the remaining system ideal. So you can see other part, when it is not in service, other part is provided by alternative path here. So therefore, this must be there. If we do not incorporate protective mechanisms for the capacitor, probably the incorporation of series compensation fails. So it should not go in that way. Technically, feasible solution means when we install a compensating capacitor, we must incorporate protective mechanisms associated to that. This way, this can be viewed as one of the best compensation for the capacitor concept for a series mode of operation. Then if you could see how that shunt capacitor concept works out here. One simulation experiment which has been taken from Power World, you can see two buses. A bus of 44.94 kV generator bus having a synchronous machine and another connected by a transmission line at far away distance. You can see the load at that point. The arrowhead shows load. There is a demand of 16 megawatt and 60 MVAR from this load. So, if there is a capacitor hooked at the same bus by 16 MVAR, which compensates the 16 MVAR in reactive load or reactive power locally, then generator need not pump that for its requirement. You can see power transmitted from the generator to the receiving end bus for a certain load 16 MW and 16 MVAR. You can see 16.8 MW, 6.4 MVAR. It is pumping a very nominal power reactive. Then 16.8 megawatt active power pumped via this transmission line reached at this bus as 16. Then 0.8 megawatt is the loss occurring in the system as per the notation. Then 6.4 megavolt ampere is pumped as a reactive power. Then that is for the reactiveness of the system itself, because the load which is absorbing 16 MVAR is locally compensated by a capacitor. 16 MVAR is compensated 16 MVAR locally. Then this reactive power what the synchronous generator is pumping is just, you see, the drop happening all along the reactive path of the system. So therefore, if the line reactance is assumed to be ideally 0, definitely this won't be injected. It is injecting at 1 pu only, means frequency 1 pu and power factor 1. So therefore, if this capacitor is eliminated from the simulation, what would happen? Definitely you will find 16 MVAR, what is being really the load here, and the drop what would happen all along the path is 6.4. 6.4 plus 16, it may be 22.4 MVAR. This generator would have pumped to the grid. It means to say this would have taken care of loss, reactive power drop, what would happen, and reactive power requirement to the load as well. 16 plus 6.4 MVAR. That would be a tremendous task for the generator to meet the requirement of a remote load via the transmission line, encountering drop across the line as well reactive. So therefore, local compensation by mode of local insertion of a compensating component is very superior. So locally 16 MVAR is adjusted here and active power is being received from this. No doubt to reach this active power, there must be active power drop as well. You can see 16 megawatt is received, 16.8 megawatt is pumped. 0.8 megawatt is still a loss happening in this line due to its resistance and other connected drops. So therefore, this is one reactive power compensation technique by shunt capacitor concept, which is simulated in Power World. I have taken example directly because it's very easy to understand. On a removal of this capacitor, definitely this reactive power needs to be supplied by the generator. On an insertion of this capacitor, this MVAR compensates automatically. There is a decrease of reactive power suddenly to a 6.4 MVAR. This way, this example by simulation so makes us to view how local compensation by capacitor by shunt is so strong in operation. Then the compensation can be split as located at two ends of the line. This makes it more accessible for maintenance throughout the region. These are the similar parameters which I am speaking about, how compensation can be done, how it is being done. Similar things are noticed here. Then moving to the another comparison of series and shunt capacitor concept. If the line voltage drop is limiting factor, see, this is very interesting comparison. If the line voltage drop is a factor which is causing you a bottleneck issue, series capacitor concept is very strong and it should be useful. The they are effective in smoothing out voltage fluctuations due to arc furnaces, welding equipment, etc. Series capacitors are not useful for volt ampere reactive equipment if it is small. So for a larger compensation, we should go for series compensation. If thermal considerations are the limitation of the line current, shunt capacitors should be used. So thermal rating, you might have seen some simulation we have used thermal rating of a transmission line 100 MV, 100 MV we have used in the model. If there is a real transmission line with the thermal limitation was imposed, suppose it is going neck to neck with which, definitely the compensation technique what would have taken is shunt compensation rather than series compensation. If the line reactance is very high, XL is very high, to compensate that, shunt compensation at either end will not help you. That is how it should be technically feasible. Line is highly inductive. A series capacitor concept is the only best mechanism which XL, XC counteracting each other would help the requirement. This way, few points which we can compare series and parallel compensation for the application. The next is synchronous condenser or phase modifier. A synchronous condenser is a synchronous machine running without mechanical load. It is a synchronous generator acting as a motor running without any shaft load. So we can see this graphical representation of its current and the power factor. So lagging power factor, leading power factor. Definitely this synchronous machine as it was seen installed at the tertiary winding of the transformer, primary, secondary, tertiary. Tertiary winding of transformer is hooked with this compensating component, and depending upon the requirement of the reactive power of the system, whether it is to supply leading volt ampere to the requirement, excite it by over excitation to supply reactive power, and if the leading var is already floating on the system, to compensate and absorb, we should run it as lagging power factor. So this way, a very flexible mode of control of excitation makes the reactive power supplement or absorb from the system is possible by this. But I was speaking about this. This is one of the conventional, very old technique of compensation of reactive power, but still it is in practice. So it's very costlier mechanism. The advent of power electronics has made a tremendous growth in compensating devices, but this is one of the conventional methods still there, even though it is a costlier. Then we can see how that power voltage control and power factor correction can be viewed. The principle of power factor correction is to compensate reactive power. As you are aware, why that power factor gets affected? If we have a power triangle, hypotenuse, adjacent side, vertical side, which is a reactive, having inductive and reactive capacitive terms, when they get equivalent of which, the concept of power factor leading and lagging comes into picture. So the power factor which is really required is because of the reactive power itself. If the reactive power in the system is highly inductive, you will notice power factor is very lagging. If the power factor is, reactive power is leading, or there is an excessive leading var, definitely power factor is superior. In line with which, if we have a load admittance, a local compensation or admittance mode of representation can be seen as if we have a load of admittance G plus JBL, then the current drawn by the load given by I is V into G or V into admittance. So it's nothing but Ohm's law. I equal to V into Y. Y is GL plus JBL, conductance and susceptance part of the system. Then definitely the compensator should see to that the susceptance is worked out. This susceptance is cancelled off. So JBL has to be cancelled. How do we do? V into GL, V into JBL. V into JBL, negative of which is to be compensated, means should be applied such that this term cancels off. So therefore, I can say a current, the compensator current IC is made equal to minus JVBL, so that lower current with the compensation is the removal of this reactive term, which becomes load current after the compensation is load current what should flow plus the compensator current which is injected. Totally it becomes V into GL. It means to say what exactly happens to the system admittance. The system admittance, The susceptance part you are eliminating by correction by your circuitry element. So therefore, the current flowing in the load after the compensation is IL plus IC. This IC takes off the second term from the product here. So therefore, this is how we can just see how reactive power injection works to see to it that the power factor become under the best observation as well voltage profile of system improves upon. Then a compensator can be used to bring the power factor to unity. Yes, definitely to control the power factor. Ultimately, the reactive side of the power triangle is controlled means power factor angle is redefined. It is the meaning a compensator can be used to bring the power factor to unity, close to the unity. A purely reactive compensator can eliminate supply voltage fluctuations or variation. Definitely, current through inductor cannot abruptly change. That is the concept of current through inductor. A reactive compensator eliminates the supply fluctuation. If you design a compensator so that the compensated reactance brings the PF to unity, then the total reactive power at that bus becomes 0. This is to say, you are counterbalancing the total reactive term by compensating the reactive term. The net reactive power in the system is being made 0. That's what you are locally compensating. Total reactive power at the load bus becomes 0 because that is set by local compensation. Now you recall back the term what we got as delta Vp in phase voltage component in quadrature voltage component that we have seen in the discussion over here. Here, delta Vp in phase with the voltage, delta Vq in quadrature. And we have seen delta Vp is Rp plus Xq by V, delta Vq is Xp minus Rq by V. So these two were the terms in phase in quadrature with the V we have seen. So that's what is being noted here. I'll come back. Yeah. So delta Vp Rp by V and delta Vq Xp by V after the assumption of that. So therefore, total deviation in the voltage, small change in the voltage is delta Vp square plus delta Vq square, which means this means a purely reactive compensator cannot maintain both constant voltage and unity power. This is the knowledge we get. If you really want to maintain fluctuations very close to 0, highly reactive compensator is required, which will not guarantee the unity power factor because system is becoming more inductive after your incorporation of inductive compensators. That will definitely make a power factor system non-unity. That's a statement as an experience of this. A purely reactive compensator cannot maintain both constant voltage. It can reach constant voltage, but it may not reach to unity power factor. This is true at the same time. So this way, how that reactive power injection comes into the notation can be viewed by this. Then we have another concept. How voltage can be controlled by using transformers. So I will just initiate this and I will close the session. So tap changing facilities are one of the important add-on to the transformer for the control of voltage, what it is delivering to the other side. Therefore, you can just see a transformer with tappings at the HV side. You are very clearly know why tappings are put at HV side, because when we have a voltage at a very large value, current flowing through a switching element, which you are tapping to the point to point, will be very low. Hence, usually tap changers are fitted at HV side only. No matter HV side is a primary or secondary for you, depending upon the application, tap changers are installed at HV side only. The reason, technical reason for that is the tap changers with a higher voltage result lower current of switching. When the tap is switched from 1 to 2, 2 to 3, 3 to back to 2 and 1 like that, when you are switching, the contacts are moving. Definitely there is a arc or spark during the movement of the contacts. That is with the nominal current. Because of voltage very higher, current at that terminal of switch is very low because of the MVA equal to voltage into current when I multiply. In that way, high voltage side, it is the installation of tap changer. So this is how a tap changer facility with a tapped winding makes the suitable contact of the winding position to get the required voltage at the other side. So another mechanism which is shown to you over here is a HV winding, which you can see very large winding. Several taps position number 1, 4, 3, 2, 1, like this way, with a special mechanism, because we have some technical difficulty of switching one contact with another with the next. There won't be any smooth flow of current. There will be a break of current and continuous. So there is a short instantaneous break and discontinuity and continuity kind of contact. So to eliminate that discontinuity,